Welcome everyone to another exciting Wednesday evening over at York Observatory, the Alan I. Carswell Observatory, bringing you all kinds of great shows every Wednesday. This week will be black holes. So hello and welcome to our online TeleTube astronomy and astrophysics program, written and presented by students, faculty, alumni, and friends of York University. This is Dr. Elena Hyde, and I'm joined this evening by Sunna, Noah, Anita, and Shannon, who will be telling you a little bit more about black holes just shortly. We are broadcasting live tonight from the Alan I. Carswell Observatory, located at York University in Toronto, Ontario, Canada. And if the skies clear up, we will be able to show you some live images later on this evening. Just as a reminder, York YouTube broadcasts every Wednesday night at 7:30 p.m. local Toronto time. You can observe, if you're listening to this later, make sure to tune in for the live broadcast and of course live chat. All right, so just as a little bit of extra introduction today, I thought I would start off this evening with a little bit of a news. Some of you might have seen in the news now, a new class of black hole has been announced. So for all of you seeing beautiful pictures of like this one here, of black holes colliding and energetic reactions, well, this was not just any black hole, this was GW 190521, and it was actually a gravitational wave detection at LIGO, and LIGO is one of the topics you will be hearing about today, but it takes quite a while to process these. So just recently, as in just today, it was published that this reaction was caused by a pair of black holes colliding. So black holes colliding are in themselves quite strange. They are very, very odd objects, as you will hear later tonight. But these black holes were particularly interesting because their collision seems to have created a resulting black hole of a size that has never been seen before. And whenever we see something we've never seen before, it's always really fun. That's basically what we're here for in astronomy. So these two Goliaths of darkness, as they say, crashed into each other about 7 billion years ago. That's about how long it took the gravitational waves to get to us. And they vibrated space-time, producing a loud, sharp chirp, which is what you'll hear if you go to the LIGO website and listen to some of their detections. This particular incident only lasted about 1/10 of a second. It's a very, very short, sharp burst, and it's left a lot of questions about how black holes form and grow. They are not well understood objects. There's a great quote going around from one of the members of the LIGO team, Dan Holtz, if you haven't heard of it before. He says this is truly surprising, which is always something you want to hear. And that will be, very, very interesting. So the black holes in this, event are not necessarily something that was thought to exist previously. This was a 17 billion light years away. You had an 85 solar mass black hole and a 66 solar mass black hole smashing together to create a 142 solar mass black hole. So that's a lot of solar masses in a black hole, and a lot of energy is actually dispersed when they collide like this. It's a really interesting event. So that's GW 190521, named after the date when it was recorded. And the publications are out today if you'd like to look them up on your favorite scientific paper browsing item. So I'll go ahead and just recommend this as future reading and happy news items to everyone, but we will get started here today, and we're going to let our staff tell you all about black holes so that you can help understand this and other interesting discoveries in context. So take it away, crew.
Thank you, Professor Hyde. Good evening, everyone. I'm Shannon, and I'm here with Sunna, Noah, and Anita, and we're here from Alan Carswell Observatory at York University. Tonight, we've got a great presentation about black holes. Today, I will be starting this amazing TeleTube by starting about what is a black hole, the parts of a black hole, and the discovery of the black hole. The black hole, an unknown and mysterious phenomenon that was theorized by German astronomer Karl Schwarzschild. For the longest time, the black hole was strongly unknown until Schwarzschild used Albert Einstein's general theory of relativity in 1916 to calculate that as long as a mass is compressed in a certain way, it can become a black hole. Yet, it took a very long time for astronomers to actually discover the black hole. The first black hole was actually discovered in 1971. A black hole is an area of space that has a gravitational field that is so long that not even light could escape it. One of the deadliest objects to ever exist that could destroy whole planets in a blink of the eye, that seizes the application of physics laws, time, and space. A black hole is made by the remnants of a supernova explosion, which is the aftermath of the death of a large star. The star must be at least 3 times the mass of the sun, which in result will make the force of gravity outweigh all the other forces, which is what creates the black hole. The way that a black hole is identified is by deflection of matter, because scientists cannot observe a black hole with direct resources, and black holes are actually invisible. The parts of a black hole. First, let's talk about the event horizon. The event horizon is the boundary in which encloses a section of the black hole in which not even light can escape it. And further, this means that the escape velocity, which is the smallest velocity required for an object to escape the gravitational attraction of another object, is actually higher than the speed of light. Another part of a black hole is a singularity. A black hole singularity is in the center of a black hole. The gravitational singularity is a point in which there's a huge mass that is compressed into an infinitely small space. At this point, density and gravity is actually infinite, and the infinite curves of space-time. The black hole theory explains that if an object were to fall into a black hole and eventually come into contact with the event horizon, they'll be stretched out in a process called spaghettification, which occurs due to increasing gravitational tidal forces. With this, scientists have actually identified accretion disks, which are typically the central body of a star that orbits a black hole, and quasars, which are very bright jets of particles that emit from a supermassive black hole. An accretion disk is actually made out of gas, plasma, dust, or particles around an object, in which the material orbiting the object's gravitational field loses energy because it is a spiral inwards with angular momentum. As mentioned earlier, Schwarzschild used Albert Einstein's general theory of relativity in 1916 to calculate that as long as mass is compressed in a certain way, it can become a black hole. Albert Einstein discovered a new theory of space-time in which he treated space and time as one thing. He explained that matter does not simply pull other matter across empty space, but rather matter distorts space-time, and it is this distorted space-time that in turn affects other matter. He also decided that he was actually unhappy with Newton's explanation of the force of gravity, and this led to his new discovery in which mass causes space-time to curve. The natural motion of things is to follow the simplest path to space-time. But since objects with mass curves, there's matter moves towards the most massive object, which is what is felt as gravity. This actually led to the discovery of warp space-time, in which it was discovered that as you move away from the center of the planet, space and time are actually less warped. In 1915, Albert Einstein published his theory of general relativity, in which he determined that mass objects cause a distortion in space-time, which is felt as gravity.
Thank you, Shannon. Now we know how interesting and mysterious are the black holes, but how do they form? Where do they come from? Stars in about 90% of their lifetime will burn hydrogen atoms into helium. Over time, they will run out of hydrogen fuel, and depending on their mass, they will have different destiny at the end of their lifetime. Smaller stars like our Sun will expand and cool down to form a white dwarf. However, in more massive stars, heavier elements such as carbon and neon can burn until iron is formed in the core. At this point, iron cannot burn into heavier elements because it needs an insane amount of energy and force to fuse. As a result, the core of the star runs out of fuel and the pressure and temperature of it increases. Consequently, the balance between the gravitational force and radiation will be unstable. In less than a second, the temperature of the core increases to over 100 billion degrees, and the star collapses under its own gravity and it blows apart in a supernova explosion. Depending on the mass of the star, it will end up either as a neutron star or a black hole. If the mass is 1.4 solar masses, we are at the limit of a stable white dwarf, which is called Chandrasekhar limit. And if the mass of the dying star is between 1.4 to 3 solar masses, it will end up as a denser neutron star. Finally, if the mass is greater than 3 solar masses, it will turn to a black hole, the densest possible state. There we go. Now we have a black hole. But well, let's talk about 4 different types of black holes. Micro black holes, also called quantum mechanic black holes, have a minimum mass of 22 microgram, which is a very, very small number. One day, it might be possible to make a minimal black hole if we will be able to compress a huge amount of matter to a tiny, tiny space and exceed the speed of light, which we know there is no speed greater than the speed of light. A stellar black hole is formed by the collapse of a star into its own gravity. Their mass is between 5 to 10 solar masses. They are very, very dense and have a very strong gravitational force that consumes the gas and dust of other galaxies around them, which makes them grow in size. Intermediate black holes might be found at the center of dwarf galaxies or very small ones. Their mass varies between 100 to 1,000 solar masses, which is a medium size relative to stellar and supermassive black holes. The picture on the right is an artist's concept from a 2,200 solar mass intermediate black hole suspected to reside in the globular cluster 47 Tucanae, which is about 15,000 light years away from Earth. Such a massive black hole cannot form just by a single star. And lastly, at the center of almost all of the galaxies, including our Milky Way, we can find a supermassive black hole. Their mass ranges between million to billion times of the mass of the Sun. There are different theories about the formation of a supermassive black hole. One of the hypotheses states that they might form when hundreds to thousands of black holes combine together, which you can see how it combines on the left side of our slides. Another theory explains that they might come from large clusters of dark matter or the collapse of star clusters. Whichever way they form, they always grow in size by absorbing gas and dust around them.
Thank you, Anita. All right, so now you know a fair bit about black holes themselves. You know they exist. But where are black holes? And how do they influence the universe around us? Feel free to check out our interview with Professor McCall when we're finished, which references a bit of what I'll be discussing here. So, as Anita mentioned, black holes often form when massive stars die, and sometimes after astronomical collisions. Aside from these locations of collisions, you may be wondering about whether there are patterns in where black holes are found, or maybe where incredible supermassive black holes are located. These two questions are, in fact, related. There actually is a recognizable pattern in where the largest of the black holes exist. It is believed that these black holes are found at the center of the majority of large galaxies. These central black holes power what are known as active galactic nuclei, or AGNs for short, within the galaxies. Before we go any further though, we must delve into what these AGN are. At the center of each galaxy, an enormous quantity of energy all along the electromagnetic spectrum is emitted, and this intense energy is, you guessed it, due to the accretion of a supermassive black hole. When this matter is gathered outside the event horizon of the black hole, forming the accretion disk with major energy already due to the gravity and friction, it is colliding and moving at extremely high speeds, thus emitting light and forming what we see as the brightest parts of the galaxies. These are considered radio-quiet AGNs. But we can't forget about radio-loud AGNs, when the immensely bright and powerful jets add to the brightness that can be seen of this region. And if the jet is angled directly towards us on Earth, we consider it a blazar. These black holes are actually some of the best proofs that supermassive black holes exist. Most quote-unquote active galaxies, galaxies with these active galactic nuclei, or galaxies with more energy than is emitted by the stars themselves, include Seyfert galaxies and radio galaxies, but they are not as prevalent as they used to be. Regardless, we ourselves once were, and will likely be eventually, an active galaxy with a black hole in the center of the Milky Way galaxy. As with anything, some galaxies exceed our expectations and manage to surprise us. For example, there are likely a few galaxies with not only one supermassive black hole at its center, but two. The Fermi Gamma Ray Space Telescope's Large Area Telescope studied galactic gamma rays over time, which typically appear in the form of the majority of energy emitted by jets of black holes. In some galaxies, the gamma rays detected actually changed periodically. This variance is suspected to be the consequence of a pair of black holes orbiting around one another. You can see an artistic view of this on the left of the slide. At the same time, last week, NASA announced an active galaxy that's black hole has influenced its entire shape. The galaxy TXS-0128 in the middle and right images closely resembles the TIE fighter spacecraft from Star Wars due to a black hole of 1 billion solar masses. The very visible jets, as you can see in the central illustrations, expand outward. Then material is pulled inward, collisions creating lobes that emit radio waves. There are gaps, too, between the lobes, possibly because the jets stopped after 50 years. 30 years later, they restarted, and its abnormal activity is currently being researched. Unlike most, the jets of TXS-0128's black hole don't actually point directly towards Earth, providing information on why we see minimal gamma rays for some galaxies, such as this one. The actual angle, which you can see in the bottom image, interestingly enough, also provides a wide span of information on its history, with both the closer lobe and the much farther lobe being visible, providing light that reaches our eyes from different periods throughout the black hole's history. It further emphasized the importance of analyzing various wavelengths along the electromagnetic spectrum, as Chandra's observed X-rays, Fermi's gamma rays, and the very long baseline array's radio waves, the last of which is pictured on the right. Each provided a unique view of the galaxy, its black hole, and their products. As I mentioned earlier, the Milky Way galaxy, the spiral galaxy in which we reside, has its own central black hole. The black hole is Sagittarius A star, featured in both images in front of you. How is Sagittarius A star found, you may be wondering, when black holes are nothing but dark matter, matter we cannot see? Because it emitted radio waves, noticed in the 1970s. Although we do have this black hole, it is, for the most part, inert, labeling us as an inactive galaxy. This black hole, 26,000 light years away, is insanely dense, 3 to 4 million times the sun's mass. Interestingly enough, just last year, it emitted radiation much brighter than ever before. This is suspected to be due to the close proximity of one of two objects to the black hole, either the star SO2 or the strangely dusty object G2. If you direct your browser to the link in the top right corner, you can view an incredible video of Sagittarius A star during a bright period of time. The Chandra X-ray Observatory has focused closely on Sagittarius A star, as has the Spitzer telescope, the former of which analyzed the lack of X-rays emitted from this black hole. These are only a few of the numerous projects targeting our black hole, one other of which is the Event Horizon Telescope, which Sunna will explain to you a bit later. Something really cool about the future of our black hole is what is predicted to occur when the Andromeda Galaxy, which also has a supermassive black hole, collides with the Milky Way galaxy in around 4 billion years. The two supermassive black holes will collide as well, coming together to create one even more enormous and likely active black hole. I know that when I first learned about these black holes at the center of each galaxy, I was curious about how the black hole influences the galaxy around it. Here, I'm going to explain some of that, namely, how black holes affect stars. Do you know that black holes typically act like coffee? They can actually stunt and stop the formation of stars, when they're active, that is. In very simple terms, stars form from hot gas once it cools down. Black holes, however, are adept at expending energy, including through jets, maintaining the extremely high temperatures of the gas, thus preventing these stars from being born, as occurs in the Perseus galaxy cluster on the right. Though this is the obvious result, it's not the only one, and this example is not like coffee at all. In other situations, black holes, particularly when they are weaker, promote the formation of stars rather than hindering it, such as within a galaxy of the Phoenix cluster pictured on the left of your slide, 5.8 billion light years away from the Milky Way. Instead of heating the gas, a limited action due to the weakness of the jets, the galaxy's gas cools as it would without the black hole present, and sometimes even quicker. Why? Because the black hole's jets push the gas farther from itself and its heating range, enabling cooling to be faster. Faster even than the matter can be attracted back towards the black hole. Although this is occurring, the Phoenix cluster's black hole is likely going to alternate between reinstating the hot temperature, thus hindering star formation, and encouraging star formation. If anything, as this example is one of the only ones that prove this occurrence, improving star formation will likely be a mere stage that does not last long at all. We cannot forget, however, how significant the formation is that black holes enable. In the Phoenix region, 500 solar masses, or 500 times the mass of the Sun, is produced each year in stars, immeasurable in comparison to our galaxy's rate of only one solar mass forming each year. Up next is Sunna to discuss with you even more about black holes, as well as how humanity sees and studies them.
Thank you, Noah. Now that you know what black holes are, I'll tell you about how you can observe them. Black holes are very difficult to observe because, unlike other celestial objects like stars, they do not emit any light. Many of the images you've seen of black holes, including most in this presentation, are artists' renditions of what scientists expect them to look like. Since you can't see black holes themselves, most of the time you must observe their effect on their environment to detect them. One way to observe black holes is when they are accreting matter. As mentioned by Noah, matter being accreted into black holes heats up to incredibly high temperatures and emits a lot of light. Much of this light gets emitted in the X-ray, which can be observed. An example of this is the clip on the left of the slide that shows the burst of X-rays emitted from Sagittarius A star when it accreted a nearby object in 2015. In addition to light emitted from the disk, jets will often be produced from the poles of the black hole, which emit strongly in the X-ray. These jets can then end with giant lobes that emit radio waves. An example of this is AGNs, which Noah talked about in the last section, but this can happen to all types of black holes. Smaller black holes may experience this when they pass through a cloud of interstellar matter, and they can even accrete stars when they pass too close to the black hole. Another way to observe black holes is by observing the orbits of nearby stars. While black holes can consume stars if they get too close, stars can also orbit the black hole from a safe distance. An example of this is shown on the screen. The left clip shows actual images of stars orbiting Sagittarius A star over a 15-year period, and the clip on the right shows an illustration of those orbits of those same stars over a 20-year period. In any case, you can observe the stars orbiting something, but just can't see what it is. Based on the star's orbits, astronomers can deduce that only something as dense as a black hole could produce those orbits and also emit no light. You can also observe black holes by the effect that they have on light, even when it's coming from an object incredibly far away. Not only can black holes influence matter, but they can also influence light by changing its path. The image on the left of the screen shows a diagram of this process, which is called gravitational lensing. If you place something like a star or a quasar behind an incredibly massive object like a black hole or a massive galaxy, the black hole will bend the light from the object, causing it to end up somewhere different from where it would normally, as demonstrated by the orange lines on the screen. This can lead to multiple images of one object. For example, the top right image is an Einstein cross, where the 4 bright dots are all of just one quasar. The bottom right image shows an Einstein ring, where the blue curve is light coming from a single galaxy that is being distorted into a ring due to gravity. In recent years, new ways have been developed to observe black holes. One way is by observing gravitational waves emitted during black hole mergers, an example of which is shown on the top right. Gravitational waves are ripples in space-time which cause space itself to expand and contract, and are generated during extreme events. The most energetic gravitational waves cause expansion and contraction on incredibly small scales, smaller than atomic nuclei, so they are incredibly hard to detect. The Laser Interferometer Gravitational Wave Observatory, LIGO, is one way to detect them, and a diagram of one of their detectors is shown on the left. Each detector consists of 2 4-kilometer-long arms in the shape of an L. One laser beam gets split into 2, with each part of the beam going down a different arm, where they will get reflected off of a mirror and return to the same location they were emitted from. They will then interact with each other, and depending on the resulting pattern, scientists can determine the distance that each beam traveled. So if one of the arms is longer or shorter, even on scales as tiny as a gravitational wave, it will be detected. LIGO is incredibly sensitive and can detect changes in distance 10,000 times smaller than a proton, so tiny vibrations caused by nearby events could cause false detections. To fix this, they use multiple detectors so that if all of them detect a signal of the right magnitude at the right time, then they have detected a gravitational wave. On September 15th, 2015, LIGO detected gravitational waves from a black hole merger for the very first time, and today they have detected over 10 pairs of merging black holes. All the ways to observe black holes discussed so far have been indirect observations, observing the effect of black holes on their environment, not the black holes themselves. In 2019, the first direct observation of a black hole was released when the Event Horizon Telescope, or EHT, released the first picture of a black hole at the core of the galaxy Messier 87, which is shown on the right of the slide. While you can't see past the event horizon of a black hole, the image shows the shadow of the black hole in the middle of the hot gas that surrounds it. This photo was incredibly hard to create because in order to observe a black hole, you need a telescope the size of the Earth, which is impossible to make. So to create this photo, astronomers used a technique known as very long baseline interferometry, where they observed the black hole using 8 radio telescope arrays across the Earth at the same time, whose locations are shown on the image on the left. This creates a virtual telescope as big as the Earth, making photos of black holes possible. Since the first black hole photo was released, the EHT has added more telescopes to its array and plans on imaging Sagittarius A star as well.
All right, everyone, we will be doing a short interlude here just to hop over to the 1 meter telescope and see if the clouds have cleared. Just a few seconds here while I excuse my, my messy screen while I transfer over. All right, and you should now all be able to see the live desktop from the 1 meter telescope. As you can see, we are trying to point at Jupiter, so it'll be a surprise we can see all together, whether or not that has worked. Now I'm just going to go and check the telescope dome very quickly before I try to take any additional images. Sunna and I believe Anita, you've both used the 1 meter before? Can you maybe tell folks a little bit about what's up tonight?
Sure. So the image that's shown right now on the screen is the sky view. And basically this section of the plane wave interface shows just a star map like you can get online or like you would use with Stellarium. It shows you a selection of some of the brighter objects that are up. So you can go on there and you can click on any object that you want to look at and drive the telescope to it, given that it's in the right position. So right now, and this is a little bit small on my screen, so I can't exactly see everything that's up, but it looks like there's Jupiter that's up right now, which of course we're trying to go to. Then
Yes, we are. That is Jupiter, and that's actually a good point. Let me just try to increase the size of the share. Is that a little bigger?
yes, that's good. Yes.
All right, let's go ahead and head over. We are trying to point at Jupiter. As you may or may not know, the sun has just started going down in Toronto. So we are battling a little bit of clouds. So I'm going to shift us over here to the live view from our camera. And we're going to be brave and try the blue filter, I think. Oh, well, ND2, Jupiter's pretty bright. Let's try it and see what happens. We're getting a bunch of clouds at the moment. So you might be clouded out in this direction. Yes, I do have quite a lot of counts on this image. You may or may not be able to see. The number of counts indicates if you are in danger of overexposing. Whoops, that didn't work. I'm just trying to adjust our light levels a bit to see if I can bring anything out. But we are pointed at one of the brightest objects in the sky. It is rather low on the horizon, and we are battling some beautiful but obstructive pink fluffy clouds. I believe this is pink fluffy clouds that we're looking at the moment.
So in the meantime, I would like to add that this is the images, these images are taken by our CCD camera, which is like one of the best cameras that we can do. CCD cameras technically can absorb a lot of light, so we can see fainter objects. And they can detect light, which is like about more than 90% of the light they can absorb it. So our eyes can only absorb 1% of the incoming light, but this CCD camera is very good. That's why we can see Jupiter and a lot of stars.
Yeah, so we would be able to see Jupiter, except for that pesky pink fluffy cloud I mentioned earlier. I don't think I'm going to be able to pull it out of the noise here. We maybe try a blue filter just to see if we can bring it out. We're awfully close to saturating the CCD though.
The CCD also has different sensitivity depending on what kind of light you're looking at. So our camera is most sensitive to red light. So it'll collect most of the light from red. It's a little bit less sensitive in green, and it's the least sensitive in blue. So with what Dr. Hyde is trying to do right now, because it's still bright out and Jupiter is a very bright object, the CCD is so sensitive that we can't look at it with the red filter because it would just completely overexpose and oversaturate the camera and you wouldn't be able to see anything. So you have to go to some other filters like the blue filter or the neutral density filters, which just block out a certain percent of all light coming through the telescope to be able to see it.
Indeed. Now we could try to point our telescope a little bit higher up in the sky. That would also give us a slightly better chance. Now Jupiter is incredibly bright, but I'll just shift back over here. You can just barely see it. If I fiddle, oh, here we go. I think I've got it. Oh, yeah, okay, so it's just poking through the clouds. I don't know if you can, if it's coming across the video chat there, but it is quite dim in the cloud at the moment. And as we're watching, I just got a glimpse of the bands of Jupiter. I don't know if you all saw that as well. Let me see if I can pause this and adjust on one image.
It was a very, very faint view of some of the bands there just for a second.
Yeah, we are battling clouds. So this is the eternal problem of live astronomy. You never know quite how it's going to turn out. Let me just try adjusting this one a little bit and see if I can bring anything out. I think we've lost it behind the cloud again. Yeah, this is the light curve that you're seeing on the bottom is the clouds in the sky. Jupiter itself is plenty bright enough to be visible tonight. So if you are in a slightly less cloudy place, looking towards the southeast, you will see a bright Jupiter up in the sky. It is nice and shiny, very bright reddish color. And if you wait even later, you will also see Mars up tonight. We're not going to be able to try Mars, although it is also very bright and only going to get brighter as we aim towards October and the closest approach, which will be a whole separate event over here at the observatory. So make sure to tune in for that. All right, let's say we give Jupiter one more chance to poke through the clouds here. And I think this is the right exposure time because we got it before. Oh, I think that's a big cloud.
If you would be able to get Jupiter tonight, we can also see 4 like biggest moons of it tonight. So if you don't know, Jupiter has 79 moons and we can see 4 of them with our telescope, even without CCD camera.
Indeed, and the moons of Jupiter are an interesting analogy as well, because there's a lot in common with Jupiter and its moons and the sun and the solar system. So the moons of Jupiter are very interesting locations. Several have water. They get their heat and energy from Jupiter, and in particular from tidal forces around Jupiter. Very, very interesting places. They're still
Absolutely.
not quite used to the clouds.
Yeah, so those are the Galilean moons. There's Io, Europa, Ganymede, and Callisto, which are visible.
Exactly, and Ganymede is the largest moon in our solar system, which is super cool.
It is even bigger than the planet Mercury.
And much more water. That looks slightly better. Let's try to see what this one does.
Yeah, and Jupiter had the most number of moons discovered just until last year when Saturn overtook it. So I believe Jupiter has 79 moons, and Saturn, there were 20 more moons that were discovered around Saturn just last year. So now Saturn has 82, while Jupiter is 79.
The battle is on. I think it's definitely a case of the more we're able to find, the more we will find.
Actually, just a quick fact about Jupiter. Jupiter cannot actually become a star, so it can't really become a star, even though it is like pretty rich in hydrogen and helium. It doesn't have enough mass to trigger like a fusion reaction in its core to become a star.
Yes, indeed, it does. It is a unique in the sense that it gives off more energy than it receives from the sun. But it is not quite capable of becoming a star itself. It would need to be several more times its size before it could hit proper brown dwarf status. And even then, if it was to try to fuse, it wouldn't have enough gravitational pressure to push in its core and create that fusion. But it's interesting because, you know, as a large planet, if it was to reach brown dwarf status, it's you actually get a state of degenerate matter in brown dwarfs, which is very, very different from what you find in white dwarfs or neutron stars, but it is a different form of degeneracy. So there's a lot of interesting things going on with Jupiter, not just its moons, but its radiation and oh, there it is. I don't know if you can see it. It's just poking through the image here. Let me just, these clouds are just tantalizing us with getting closer and closer to showing us Jupiter here. If I increase this a little, you can just see we're just getting the fuzzy bits of Jupiter coming through. It is battling a cloud. I think if I open the door again and go out, we'll probably see that nice big pink fluffy cloud still out there. So hopefully that is coming through on the live images. So I think, well, oh boy.
That looks great. You can definitely see the
so much
bands
better.
there.
The cloud moved. All right. So does anyone see any of the moons? I don't see what's coming through. So we're just battling the clouds here and the setting sun, but you can see that even in these conditions, we are able to show you the planet Jupiter. And it looks like we have, I call it maybe 2.5 cloud bands showing up here.
Yeah, looks like that.
And for those of you who don't know, it is actually a very interesting legacy put forth by none other than Carl Sagan, who proposed that there might even be life forms in the cloud bands of Jupiter. I believe that the going theory was that with the amount of water and chemicals in Jupiter's atmosphere, you could have locations that were close to being reasonable for some forms of life. So perhaps, you know, flying cloud creatures of Jupiter might be out there somewhere in these bands.
Absolutely.
All right, folks, we actually have a picture of Jupiter despite the clouds. I hope you are all enjoying this as much as I am.
Actually, the clouds on Jupiter are only about 50 kilometers thick, I think.
There are multiple layers of clouds. It was actually a very interesting experiment that they did where they tried to drop, oh gosh, what was it? The probe that went into Jupiter's cloud bank. Trivia astronomy question. Dropped into the layers of Jupiter's clouds and tried to map what was underneath the surface. And it's more clouds. It's different forms of clouds and different types of gas than we are used to here on Earth. Because of the large mass of Jupiter, it can reach very interesting states. And the core of Jupiter has a few different possible theories of you know, everything from super dense forms of you know, liquid metal to all kinds of different stuff. So it's not thought to have any kind of a solid surface, but it will have a lot of variety in the different kinds of clouds and structures inside there. All right.
Yes, and if you're interested and you haven't already done so, feel free to check out some of our previous TeleTube videos. We have many on some subjects, including this one, such as our planetary weather, where you can find out more about Jupiter and its clouds and potential life and all that sort of stuff.
Indeed, that is actually an excellent point. So I think that we will probably wrap up our viewing for tonight with this lovely image of Jupiter coming through the telescope here. And let me just try one more, see if we can do even better, or if the clouds come back. Oh, actually, that might actually be better. We are saturating a bit, as you can see. But if I adjust the levels, we are now getting a fairly bright image of Jupiter coming through. You might even need to be thinking about switching filters if we were going to try to image this all night. There we go. This is possibly the winning image for tonight. Of course, it will only get better, but we can only stay online for so long. So I hope you have all had a wonderful evening. Let me just go ahead and transfer back here, provided I can find my screens. And again, please just excuse the slight interruption here. There we go. Now we're going to be wrapping up this evening's presentation. I hope you enjoyed our live images from the 1-meter telescope here at the Alan I. Carswell Observatory. And as mentioned, we do have an entire episode in our live stream recorded sessions, and all of our sessions are recorded. So if you'd like to go and listen to something about planets, feel free to look that up inside our live stream playlist or on our videos section on YouTube. All right, I believe we have a short outro. Sunna, was that you?
Yes, it was. All right, so
take it away.
Well, everyone, you've been listening to the Alan I. Carswell Observatory's weekly TeleTube broadcast, the Astronomy and Astrophysics program written and presented by the students, faculty, alumni, and friends of York University. The hosts this evening have been Noah, Anita, Shannon, and myself, Sunna. Make sure to leave any comments or questions in the comment section of the video. You can always connect with us on Twitter at the handle @YorkObservatory and check out our websites for show notes, content, updates, and contact info at observatory.info.yorku.ca. Thanks for tuning in, clear skies, and have a good night.
And again, we will go ahead and stay online for about the next 10 minutes to take your questions in chat. Hope you've had a wonderful time.